Okay, guys. Now let's looking at compressibility. So even the word itself, it explain the concept about it. Its compressibility. The compressibility. The how you can be able to compress, or how to compress something. Now, if something is compressible. So here the side the degree of compressibility of a substance is shown by the isothermal bulk efficiency. So the isothermal bulk efficiency, we are talking about this K. So the isothermal bulk efficiency, or by it is the one that is represented by K, right? So this isothermal bulk efficiency, it's also can be calculated, or can be said is the change in what is the change of the is the change in what in pressure, right? So the change in pressure over the volumetric strain. So the volumetric strain, it's that this is the bulk efficiency. So now, would they say that this compressibility, the compressibility of a substance can be shown by what? By the isothermal bulk efficiency. And then by looking at the isothermal bulk efficiency, we find that the isothermal bulk efficiency is what is the change in what in in the pressure over the volumetric strain. Remember, when you're talking about the strain on science, we say strain something like this. Strain was equals to the change in length over the original length. This is what this is the change in what change in is the strain, sorry. So the strain is talking about the change. Let's say now we were applying a certain force. Let's say we're applying this force of what? This force of 200 Newton, and the original length of this piston is 0.3. And then when you apply this force, there will be a change in what? Change in this length. So the change of this length over the original length, we call it what? The volumetric strain. Now, and then sorry, it's strain, not the volumetric strain. But then now, if we're talking about the volumetric strain, we're talking about let's say the volumetric strain is, we're talking about the change in what? The change in volume over the original volume, right? So this is the volumetric strain. So not this one. This one was on linear. So now the volume, or we know the volume of what? This is the diameter of this piston. So the diameter, we can get the area times this height, we can get what? The original what? Volume. And then when we compress with this force, then if this force or this piston can be able to compress, it will have what? The change in area. So that will give us what? The volumetric strain. So the volumetric strain, now said the volumetric strain is actually E over so the volumetric strain, it's E, sorry, it's E V, certain something like this one, but this is E V, which is volumetric strain. I don't know the type of a textbook that you are using, but it can differ with textbook, but the concept is still the same. So we're still explaining what the bulk modulus. So the isothermal bulk modulus is the change in pressure and intensity, or the change in intensity pressure of the substance over the volumetric strain. It gives us what? The bulk modulus. Or we can also calculate the bulk modulus by, say, it's equals to 1 over beta. So where beta is the coefficient of compressibility, this one is the coefficient of compressibility. Now, so the coefficients of one divided by the coefficient of compressibility will give us what you call will give us the bulk modulus, and the bulk modulus will be given by what the SI unit will be in Pascal, because it's what is pressure over strain. Strain doesn't have unit. It's both the unit of volumes will be in cubic meters, so that when you cancel, that means the volumetric strain doesn't have what unit. That means the bulk modulus will have what will use the units of pressure. Now, so the bulk modulus over then give us what uh, strain. So now the bulk modulus, which is going to be K, can also be calculated as well. Oh, for force we know that sorry, pressure, we know that pressure is force over area, right? So if force over area, it give us what you call, it give us pressure, and then pressure now is what pressure is this pressure over the strain, right? So we can then say this K can also be given as what as pressure multiplied by uh, the change in what the change in, this is the change in volume. The change in volume, it has something like this. So the change in volume over the original volume. So we just drive this one from here. Yeah? So we say that this is what? This is pressure over, yeah? Pressure over strain. Strain, we say, is change in what? In volume over, sorry, as change in volume over original volume. This is original volume. So then when you multiply it, remove this one, and then you're going to have P times V over change in V. And then you can also put this one, if you don't have the pressure, you can put what? You can put the force over area multiplied by the volume over change in volume. So this is going to still give what? The bulk modulus. So the bulk modulus is at its K. So now let's look at this example. So this is our bulk modulus, which is 1.9 Pascal. So let's do an example. So here, if they say calculate the pressure in the system, so the pressure in the system, we're going to say pressure will be equals to force over area. So what is the force? The force is 2000 or 200 Newton over the area. The area, it will be what? Area is always area of a cylinder. It's always pi v squared over 4. This is area. And then our diameter is 0.02. And then we can then multiply by 4 here and get what? Say pi multiplied by 0.02 squared. And you get what? And you get our pressure, which our pressure will be equals to 6.37 megapascal. So this is our pressure. And then number 2, if they say calculate the volumetric strain. The volumetric strain now, we say the volumetric strain, which is this one. Where is it? Here, the volumetric strain. Volumetric strain is that is equals to the bulk modulus is equals to the pressure over the strain. So we can say K is equals to pressure over EV. This is what this is the volumetric efficiency. So the volumetric strain, and then we say the volumetric strain will be equals to pressure over the bulk modulus, and then our pressure is 6.37 times 10 to the power 6 over our bulk modulus is here, which is 1.9 times 10 to the power 9. And then we can get what? We can get our strain. Our strain would give us what? 3.35 5 times 10 to the power negative 3. This is our strain. And then if they say calculate the change in what? In volume. The change in volume, we get to our volumetric strain. We say it's a change in volume over the original volume. Now, then the original volume, always the original volume is equals to pi d squared over 4 times the stroke length. So it's the diameter, the stroke length, and then we can get that. So the change in volume will be equals to the volumetric strain, which is 3.35 times 10 to the power negative 3, multiplied by pi times 0.02 squared over 4 times our stroke length, which is 0.3, and then we get that, we get our volumetric strain. So our change in volume, yeah. So the change in volume is going to be 31.56 times 10 to the power negative 8 cubic meters, right? So the last thing that they can ask you to calculate the linear displacement of the piston. So the linear displacement of the piston, we're talking about what the we know what is displacement is to displace something. If now this is the original height, and then if they say if you move this piston maybe if you move this piston to this to this point, so that means you have displaced now this piston to this point. So the linear displacement now will be here. This displacement is the same as the stroke length, but then now to get this one, you need to calculate by using what? The change, because now this is the change in volume. That means it's going to be the change in volume is equals to the area multiplied by the change in length. That means this volume, this area, because the diameter of this container doesn't change, and then the only thing that changes is the length when you moved from this point to this point. So that's when you know that this system is compressible. Yeah? So when it's able to move from this original point to this point, so the linear displacement of the piston will be this L. So this change in L will be equals to the change in volume over the original answer. So this is your change in volume over the area, which was calculated somewhere here. So so this is so stay tuned to the next one, when we're going to calculate when we're going to discuss viscosity now. So I think we will do both the viscosity and kinematic viscosity on the following video. So feel free to send me questions so that we'll be able to answer those questions. So if I have time, I will be able to answer those questions. So sorry for those people that I didn't respond in time, but then I will make sure that this time around I will answer question. Okay, before we move on, we also have on the compressibility. Let's look at what you call the effective of the bulk modulus. So the effective bulk modulus. So the bulk modulus, it's what? It's our K. So the bulk modulus, the effective of bulk modulus. So This effective of bulk modulus will be given by the formula of this one. E, remember I will say P is the coefficient of bulk of compressibility, which is equals to now E over K, right? So at first we say K is equals to 1 over P. It's the same thing. Then now we just make P subject of the formula. So this is can also be determined by what? By 1 over Kc plus 1 over Kl plus this Vg over Vt, yeah, into 1 over Kg. So the effectiveness of a bulk modulus. Now let's look at the bulk modulus. The effectiveness. They said here when a force is applied into a piston, let's say this is the piston now. So when a force, let's say a force of F, it's applied into this piston. So into a piston of a cylinder filled with liquid. So a spring effect or a play is experienced on the piston. So when you apply a force that is on a piston filled with what with liquid, so you will experience a certain spring effect. So that means a bouncing effect, maybe a sponge effect. No? So this sponge effect is caused by what? By the compression of the liquid inside, and it's also caused by the compression of air that is trapped inside the cylinder. So if there's air trapped inside, there's also is going to be compressed. And then another thing is going to be caused by what? By the expansion of this wall of the cylinder. So that means that the spring effect is going to be caused by three things. It's either the compression of what? Of this liquid, the air that is trapped inside here, and also the compression of what? Of these walls of the cylinder. So that's why when you calculate now the effectiveness of bulk modulus, the effectiveness we're looking at each material. Name. So when you're looking at each material, this KL, this is the bulk modulus of liquid. No, so of the liquid inside the system. Sorry, liquid. So, and then when you're looking at this KC now, this one is the bulk modulus of the material. Um, uh, the material that is used here, which is we're looking at the material of this piston. So this KC is always equals to KC will be always equals to E over 2.5. So this E is now Young's modulus of steel or Young's modulus of a material. So if this piston is made of a copper, you know the Young modulus of a copper. If this steel is made of a steel, it's going to be a Young modulus of a steel. So this is going to get at your bulk modulus, which is going to be used here, right? And then this is the bulk modulus of liquid, is the one that we calculated before. And then when we're looking at this VT, your VT is going to be your total volume inside the inside this inside the piston, right, or the cylinder. And then we also have this Vg. This Vg is going to be the volume of the gas trapped inside this one. So the volume, this one is for gas, or for, let's say, air that is trapped inside the system. This one is the total volume of what? Of the liquid inside the system. And then the last one this 1 over k. This 1 kg is what? It's your is your back modulus of m. So k is always going to be alpha multiplied by p, right? Which your alpha is always going to be equal to 1.4, right? And then multiply by the pressure to get what? To get this k. This is the bulk modulus of A, right? So remember, we said the effectiveness of this, the bulk, the effectiveness of bulk modulus of this liquid, of this system is caused by three things. Is the expansion of the material inside, outside, is where we're looking at Kc, the material, which is going to be Young's modulus over 2.5. And then it's also caused by the compressibility of this liquid, which is going to be what? Which is going to be 1 over the bulk modulus of liquid. And then lastly is what is caused by the air that is trapped inside. The air that is trapped inside is going to be the volume of the air inside divided by the volume of the total volume of that, of the liquid, multiplied by what? By the bulk modulus of the air inside the system. So this is how you need to calculate um your volume, sorry, your bulk modulus, right? So in our case here, so they say that this bulk modulus of air is always going to be 1.4 multiplied by the pressure of the system, right? So this is the effectiveness of the of the bulk modulus inside the system. So now, so they said again, the interaction of the spring effect of the liquid and the trapped air and the mass of the mechanical part must be considered when compression, when compression compressing a liquid. So the effectiveness of the bulk modulus is calculated as follows, which is this one. So you consider all three things that are causing the bulk modulus. So now, let's do a quick example. A quick example to get what the effectiveness of bulk modulus. So the effectiveness of bulk modulus. Okay, let's use this one. So say the length is 0.7 meters, and here the diameter it's 0.05, and then we're applying a force of 2 kilonewton, right? So now you are given what the the modulus, or the bulk modulus of liquid, which is 1.9 kilopascal, and then we have what the Young's modulus of the cylinder wall, which is 2.03 kilo gigapascal, right? And then again now they're given what 2% of what 2% of air in what in the system, right? So if they said there's 2% of air in the system, that means volume of what of air over the total volume of what of the liquid is equals to what 2 over 100, right? Okay, so now the question said, find the effectiveness of the bulk modulus of the system as shown. So we need to calculate what this bulk modulus of the system. So we do have what KL, which is this one. We don't need for that one. And then for KC, we need to calculate the KC. So we say the KC, it's what? We say the KC is given by the Young's modulus over 2.5. So it's going to be 2.03 over 2.5, and then you get what? You get your 0. Um, 0.836 gigapascal. So this is Kc. So you have Kc, you have Kl. Now you need to get this one. So this Vg, you do have also this one. Now you need to get what? 1 over, we need to get Kg. So this Kg now, we say the Kg is what? Is alpha multiplied by pressure. So we need to get the pressure. Pressure is equals to force over area. So our force that we are applying is 2 kilonewton, which is 2 times 3,000 multiplied by the area, we can say multiplied by 4 over pi times 0.05 squared, and then you get the pressure of it, pressure of 1.02 megapascal, and then that means kg now is going to be 1.4 multiplied by 1.02, and then we get what? We get 1.428 megapascal. And then now you can be able to get what? This one. Then now you can say your effectiveness, your bulk modulus, effectiveness will be 1 over Kc. It's what is this one, which is going to be 0.836 times 10 to the power 6 plus 1 over KL. It's what is the one that we are given them, which is 1.9 times 10 to the power 9 plus the ratio, which is this one, 2 over 100 into 1 over kg is 1.428 times 10 to the power 6, and then you get that your effectiveness. Right, so your effectiveness of the back modulus is going to be 63.58 megapascal. Right, so this is what, this is the um this is the effectiveness of what, of bulk modulus. Right, so this is what it's happening. Yeah, so thank you. This one was too long. I will try to summarize the next one.